Alrighty, so welcome to my Student Scholar Days presentation. My name is Schehrer. I am a mathematics major, like Scott before me, with a physics emphasis. And my presentation is going to be modeling a single wrap, three-dimensional ferrite inductor. So before I start off, I have been an intern for Sandia National Laboratory since May of 2017. So everything I'm doing in this presentation is sponsored by Sandia and solely for them. And so my main job was to computer model and reproduce laboratory results for my current organization that I'm in. And specifically, that is the single wrap toroidal inductor with a ferrite core. So first off, as you might know, what is an inductor? So an inductor is basically an electronic device that stores magnetic energy, or a magnetic field is an energy. And it generally can be a loop of wires or coils around air or some magnetic material. And they're used in a variety of your electronics today: TVs, radios, power devices, and other such things. So how did I go about modeling, and what is the program I needed to use to model and create laboratory results? So what I used was COMSOL Multiphysics. COMSOL Multiphysics is a highly sophisticated not three-dimensional, but modeling program that models scientific and engineering problems. And it can do just about anything you want. You think of something scientific, an engineering problem, you can probably solve it with COMSOL. And the nice thing about COMSOL is you're able to use a graphical user interface, or a GUI. And rather than, as you think of maybe programming and coding, it's more in the GUI. So you're building and you're applying different types of physics and other type things to the model rather than specifically coding certain problems. So how does it work? So basically it's a finite element method which goes through and uses your problem, and it sets it up in a partial differential equation. And these partial differential equations, or PDEs, can be solved analytically or by hand, so I couldn't just sit down and solve them on paper. So we can solve them numerically using COMSOL. And it's an approximation, right? So it's not going to be exact, but it's a very, very accurate estimation. So to do this, you create a mesh. And if you think about this mesh as a fishing net, if your dad gave you his salmon net and said, go catch minnows in the pond, it's not going to work. You're not going to get anything very accurate. But the smaller you go, the more minnows you catch, and the smaller and the finer mesh you'll go. As you continually get smaller, it will get more accurate. But there is the downside of this mesh, is if you go too accurate, it takes up a lot of computing space and memory. So you kind of have to find an in-between to the results that you need. So the build and the meshing. So I use COMSOL's built-in computer-aided design, or CAD program, to build the inductor, and it's a pretty simple build. We have the toroid here, where it just looks like a donut, and it's shaped to size of the inductors that we use in the lab. And so it's about 5 millimeters across and has a width of about 1 millimeter. And the wiring we use here is 30 gauge copper wire, or about 0.25 millimeters, with a diameter of 0.25 millimeters. And the mesh I used kind of varies depending on where I am. So I use a triangular mesh, which gets smaller and is more focused on the areas of interest right around this coil, and gets gradually bigger on the outside where there's not as much going to be going on and it doesn't need to be as scrutinized. So before I go into my results, I want to talk about alternating current, which you've probably seen on many of your electronic devices. You see AC this, AC that. And for it to work, I induce an alternating current anywhere from 1 kilohertz all the way up to 7,500 kilohertz. So it's a pretty big range that we're looking at. So for example, this is just a standard AC current. So for example, this is 1 hertz, and this is just 5 hertz. So you see in one period of the 1 hertz, there's 5 for the 5 hertz. And so to make the problem, or make the model run more efficiently, we need to input a couple of physical properties of the ferrite, which a ferrite is basically an iron oxide, so Fe3O4. And this includes a BH curve, which I'll cover in the next slide, and a complex permeability, which will be covered in the next slide too. So the frequency, we need to input what kind of frequency we need, and then two constants, the permittivity and conductivity of the material, which is just taken out of the book for permittivity and conductivity. So the BH curve is a pretty interesting curve. It's known as a hysteresis loop, and it's basically due to the alternating current that we induce on it. So when you induce an alternating current on to the inductor, it saturates this material. And so you can kind of see how when it goes up, that's where the top of the humps were in the previous slide, and then as it goes back down. So this material at 1 kilohertz, which is actually from laboratory results, this hysteresis curve, is going to look similar. And they're going to change as we increase frequency. They'll become saturated faster and have a bigger amplitude between them. So it kind of varies throughout. And so the BH curve is basically the graphed on the x-axis is the magnetic flux density, and on the y-axis is the magnetic field. And the next part is the complex permeability. So we can input a relative permeability that we're given with the material itself when we buy it from the producers, and that's just 2,500. But because we're running it at such high frequencies, we get a real and an imaginary permeability. You might think, how can you use an imaginary permeability in your model for it to run? But basically is because at high frequencies, the permeability is proportional to the magnetic field and the magnetic flux density. Whereas with high frequencies, they're going to become out of phase. And this in physics terms are known as phasors. And it creates a phase between them, and there's an angle between these two permeabilities. So to find this, to find the imaginary and real permeabilities, we can use Euler's formula, which gives us the ability to find both the real and imaginary permeability, where this is the regular permeability, which was 2,500, and mu sub 0 cosine theta, which is the real, where mu 0 is just a constant of science, where it's the permeability of free space, or 4 pi times 10 to the negative 7th henries per meter. And we have our imaginary, mu sub 0 I sine theta. So we have our real, mu prime, and our imaginary, mu double prime. And it's interesting how they work. As you raise frequency, the real permeability starts high, and as you increase frequency, will drop lower, where the imaginary permeability starts low and works high. So they work against each other. So what are the results? The results, we can do a couple of things which are pretty interesting. First, I can run the model, and I can export data onto Excel and directly compare it to our experimental results, and kind of compare and see what we have. But the beauty of COMSOL is we can also do three-dimensional surface plots, which gives us an idea of what's happening at the surface of this inductor when we apply this current, whether it's 1 kilohertz or 5,000 kilohertz. And specifically for this, we can look at the magnetic flux density, the core loss, and temperature, which I'll cover in the next couple slides. So the first one is inductance. This was one of the first, basically one of the first properties that I was trying to look into. We tried to find, we had basically another computer model that would, you could put in the inputs of the inductor and solve for inductance. So I started with inductance as the first one. And inductance is basically kind of, as the current rises, that will store energy and will have a potential drop in the voltage, and then as it opens, we will have a drop, or a raising of potential. And so it started out with this, and I was anywhere between 10 to the 5th power off, and So it took a while before I was able to really get pretty accurate results. And you'll see that the experimental is in blue, and the COMSOL is in orange. So it starts out at lower frequencies, a little off, but it eventually converges quite well with the experimental data. And I'm not sure exactly why. You'll see that in all of them, why at lower frequencies it doesn't work as well, but as it converges to higher frequencies, it converges quite well. And so it converges quite well, but we want to also look at why does the physics work? And using a formula from the labs, it's basically dependent on the real permeability. So as the real permeability is the highest at 1 kilohertz, and as we decrease, the real permeability decreases, thus decreasing the slope of the graph and matching our results. So the next issue I looked into is the magnetic flux density, or the magnitude of the magnetic field. And so again, we have the results here. This time it decreases as we increase frequency. But then the big thing that we wanted to see if the physics works was if we had a 1/r trend, where r is the radius of the inductor, and that's by using Ampere's law. So it should, as you start from the inside and work out, as the radius increases, you should see a drop in magnetic flux throughout the inductor, which we see here. You see in this line graph, which is basically starting from the inside to out, and we see just kind of on the color codes of the inductor itself. The next aspect, which isn't nearly as interesting just because the properties of copper are pretty well known, but I'm able to analyze the voltage and resistance of the coil by having the current that I inputted manually at 1 amp, and using Ohm's law, we can figure out the voltage and resistance. So I found resistance by having COMSOL solve for the resistance, and then using Ohm's law, where V equals the current times resistance, which the current was 1 amp, is the max induced voltage on the coil. And so then the last piece of information that is, in my opinion, most interesting of what I was looking at was the core loss. And the core loss, you'll see, is pretty accurate and was the most accurate data set that I had throughout the modeling so far. It's anywhere between 2 to 4% off in places. But you'll see that it's measured in watts. And watts, as you might know, is a measure of energy. So a measure of energy, we think, what kind of energy is it? So it needs to be expelled as heat in some way. And it makes sense as we increase frequency, there's more oscillations happening, and we are getting a much higher core loss as we increase frequency. And the surface plots really kind of help you see what's going on too. We still have a similar 1/r trend on this inductor, as you can kind of see, but it's a much more complicated calculation than just using Ampere's law. But another interesting look is where we saw magnetic flux was pretty symmetrical throughout. We have this coil here, and where the coil has a pretty great effect right on the sides, whereas on the other side of it, it has almost no effect. So the core loss can be related as heat. And to solve for this, it is basically the sum of hysteresis loss and eddy current loss. And they are both different in their own way. Hysteresis loss is more on the inside of the inductor, and eddy current loss is on the outside. And hysteresis basically is, if you think about all these magnetic material inside, thousands of these little domains, and before you stick it into the instrument, it's randomly spread about. But as soon as you add current to it, it's going to align itself with the shape of the current. So when current is positive and it's flowing one way, the magnetic little subdomains, or what you'd like to call them, are going to align with the current. But the moment the current switches and reverses because of this AC current, it'll flip around and flip the other way. And it's almost instantaneous, but not all of these little domains flip. So we have a couple of these domains that are straggling, and they need more energy to get flipped. And this causes the core loss. So it causes more work to basically flip. And this work then has to be turned into is some energy that's just dissipated as heat, which we can't measure in the lab. We can measure all the physical properties, but we can't measure heat. And the next is eddy current. So eddy current works on the surface of the inductor. And if you think about a river where if you had a rock in the middle and you had the current going one way and the current goes the other way, there's these little swirls. And it's basically acting the same way. As the current is flowing around the inductor, there's these eddy currents that, again, go circular around the current. And then when it switches, they switch. So this causes a core loss as well, which again is dissipated as heat. And this is a pretty interesting picture. So here's the heat flux magnitude. So just looking at the heat, and we see that where the coil is located, copper coil, we have a bit of discrepancy here, but then as we get farther away, it's pretty symmetrical, and it kind of equilibrates to how it dissipates the heat in the inductor. And the next portion so we can't measure in lab is the temperature, and that's one of my advisor at San Diego is pretty interested in is how these inductors heat up and how hot they'll get. So the temperature graph that I had isn't very interesting. You can make it look kind of cool, but in reality, it's not getting very hot. The plot is anywhere between 0.03 degrees is how much it changes on the thing. So not really interesting, but the temperature gradient is kind of interesting because we can see again where the coil is. We have a much higher gradient of the temperature, and that's just because copper has a bit higher conductivity and heats up faster than the ferrite. But we can see where it's located has a pretty good effect on the heat. Whereas you go around, there's not as much heat change around it. So there's a lot more research to be done. I'm still working with San Diego, and I'm still modeling today, and I'll be heading back again at the end of May. And so there's a couple more things that I want to do for this model. And this includes running my own BH curve, because right now I'm inputting it, and I can get a lot of those physical attributes from the BH curve that we input. But if I'm able to create my own BH curve by, I have to code a bit and create, which will create its own, and I can use those to then input into the model that I'm using now, which will make it self-sustainable and give us an idea about not only materials that we don't know about, which is what we're looking into is an iron nitrate and different nanomaterials that are of interest. So we'll be able to predict how this inductor is going to act before we actually have to make it, because besides the ferrite, the materials that we're interested in have to be made. So they're taking them and pressing together and making these inductors themselves. And here's my sources. And that is it. Are there any questions?
Most of the things you showed me while you were doing this involved multiple wraps, and yet the thing you were showing us through most of the talk was a single wrap. How much of the studies, what fraction of the studies have been done with a single wrap versus maybe 4 or 5 coils?
So I just got data with 4 coils last month. They've been working on it. So they actually improved the machine that they use, the BH looper, and they're adding more coils. But really the first was, I don't know where they got this machine to begin with, but it wasn't very accurate. So they used this single wrap to get pretty accurate results with the ferrite, just because it's a pretty well-known material. And using the multi-wraps, which I had showed you before, was just kind of like seeing how it worked for my advisor, and it was kind of cooler than just a single wrap coil.
So when you say they got some new machine, you're talking about in the lab, this is the experimental?
Yeah, this is the experimental lab. So it started off with,
catching up with you, basically.
exactly.
But the ferrous oxide, I think you said it was?
Mhm. The core.
Core.
Mm-hmm.
And it was the wire that was copper.
Yep. So
You were modeling heat loss in copper as well. It looked like in the heat loss, your core loss picture, there was coloration to the
Yeah, so I have it look at everything when I do that surface plot. So I could pull out the wire, but the wire is going to have its own heat as well, just because adding the current to it. So seeing how not only how the coil heats up because of the core loss, but also because of how it heats up with the coil as well.
Just plain resistivity.
Mm-hmm. Any other questions?